welcome everybody. I imagine we always talk about 60 minutes the night before, and I'm not going to spend much time on it, but I was intrigued by this fluvoxamine, an antidepressant that is now thought to have some benefit for people with the COVID-related illnesses. In a small randomized trial, 80 people who got the drug, took the drug, none of them got sicker, but of those on the who didn't take the drug, 8% deteriorated. So that was considered pretty significant, and they're going to do further studies. That was an interesting aspect from 60 Minutes. Well, coming to today's speaker, Anchor encouraged us last fall to invite Elizabeth Maroon, and I'm so pleased to take his advice. Dr. Maroon is interested in how the ocean influences climate variability and climate change, with an eye toward applying our understanding of coupled ocean atmosphere processes to the analysis and improvement of climate predictions that are either inter-year or interannual, as she calls it, or decadal. And she uses a variety of tools, including climate models. And she tells me that she's very happy to have come to the University of Wisconsin a couple of years ago, just before the pandemic hit us. So we're delighted to meet you. If we can call you Elizabeth, Dr. Maroon, and okay, informally, and the slides are yours.
Great. Thank you very much for the kind introduction. I've only been here in Wisconsin for a little over a year now, so I don't really know anyone. I got here before the pandemic, and I figured by now I'd be making friends in the community and giving more talks like this, but well, the world had other plans for us.
Yes.
So I'm very happy to talk about one of my favorite things, which is Atlantic Ocean circulation. Before I do that, I'm going to start off with a brief video from NASA to sort of, just sort of like show us why we should care so much about ocean. So I'm assuming you can see that now. Richard, give me a nod if you can.
Yes,
Great.
I can.
So this is a video from NASA, and they base it on observation of the height of the ocean, and then they put it into a model to fill in all the blanks. And it's just an absolutely gorgeous animation that shows us the complexity of our oceans. You can see all these little currents. They're tracing along where the weather in the oceans. This is ocean weather. It's a lot smaller scale than what we have in the atmosphere. But you can see a lot of features that are really coherent. So all of these little eddies, you can see in general, things tend to move up coasts in that way. A lot of fun things going on the equator. You get these little beautiful rings, especially these that swoop around Africa. Those are called agulhas rings. And then things get really complex in the Indian Basin as we come up here. You can see all these coherent currents, the split direction depending on where they are. Big eddies up in the Indian Basin, and those get affected by the monsoon circulation seasonally. And then as we come across, we're going to start to get into Pacific Ocean, which is an especially important place for our climate in general. So we have all these beautiful little eddies spinning around, but in the long-term mean, what you get is these currents, these western boundary currents. So this is one called the Kuroshio, and then it extends out into the Oyashio. So when these eddies all get meaned out, they carry water across the Pacific. Now we're in the North Atlantic. And now if we come down here to the tropical Pacific, some of you have probably heard about El Nino Southern Oscillation. So these currents in the Pacific Basin are really key for that whole phenomena, and they affect climate worldwide.
Could I ask a quick question?
Sure.
I gather the Sargasso Sea is noticeable for its lack of eddies. It's sort of a blank area in your imagery there.
Right. So you have the most eddying activity where you have very strong temperature gradients. Okay. So where you have warm next to cold horizontally, that's where you're going to get the most eddies. Okay. So when you're near a continent, continents tend to be a very different temperature from the ocean. So you'll get a lot more eddies. When you have strong jets above, you'll get a lot more eddies, and Sargasso Sea is just not in one of those locations.
Sure. Okay, thank you.
So then we come down to Antarctica and you'll see the Antarctic Circumpolar current. So all of these eddies and the timing to go from west to east. And that feature is really important for setting the global ocean circulation. If we didn't have that whole current, we wouldn't have the thermohaline circulation that we do. And we're coming back around to Australia again. Lots of eddies. You can see stuff going around what we call the maritime continent, this whole area, Indonesia, Papua New Guinea, all that. Here you can see much more clearly what's going on in the tropical Pacific. Can stop that and scooch back. Scooch back there. Yeah, so this is really important for El Nino. The fact that we've got these big currents going across from the east to the west along the equator. But anyway, this is just, I think, climate is important for many reasons. It affects how we live, where we live, it affects ecosystems. But from the ocean and its impact on the climate is also something that's just very, very beautiful. And this very nice animation put together by the scientists at NASA is a great way of showing just how beautiful the circulation is and how beautiful fluids can be. So I think it's always useful to remember what a wonderful world we live on.
Mm.
So let me change back. Okay, so as Richard said, I'm Dr. Elizabeth Maroon. I'm a new assistant professor in the Department of Atmospheric and Oceanic Sciences. I just started there quite recently, right before the pandemic. And I teach physical oceanography and data analysis for geoscientific data. So today I'm going to be talking about more specifically the Atlantic Ocean circulation and climate. I don't focus only on the Atlantic, but it is my favorite place if I had to pick one. So a roadmap for today's talk. Part one, I'm going to talk about why do we have ocean circulation? Sort of just an overview of here's what the main circulation features are in the large scale. Why is the Atlantic a really central place? And why is the Atlantic so important for climate? And then part two, we'll take a bit of break if there's any conversation that we want to have in the middle. And then part two, we'll talk about climate change and what happens when we push, at least for the ocean, what happens if we emit greenhouse gases and push the whole Earth system out of equilibrium? And what does that mean for the circulations of the Atlantic? And then more generally, what does that mean for us if things in the Atlantic get messed up? So the reason we have weather in both the atmosphere and the ocean, and the reason we have climate is because it comes down to the fact that the Earth is round. So if here on the left, we've got an image of the Earth, the yellow arrow represents sunlight coming in. We have more energy that hits the equator and the tropics because it's direct on to the sunlight's beams than in the poles. And so this sets up the visual light. We have more energy coming in at the tropics and the poles, and nature abhors an imbalance. So the whole goal of this, just having this extra energy at the equator, the Earth system is going to try and move it try to get rid of it, come back to balance. The first way it does that, the easiest way you could say, is okay, we're just going to send this heat back out to space. So this would be infrared radiation mostly. And it can do that anywhere that the Earth is warm. And that's the first feedback that happens because the Earth gets warmed. But that's not enough. You can emit radiation pretty evenly around the entire planet. But it's not enough to get rid of that imbalance that we have too much energy in the tropics and too little at the poles. So the second thing that happens as a result is that the Earth system will move energy from the equatorial regions to the poles. It'll in any way possible it can do it, it's going to try and get energy away. And so what we have here is a graph of heat transport. Where it's positive, that means things are moving poleward. So this blue line here is poleward energy transport. Anywhere it's positive, it means energy is going that way. So in the northern hemisphere, here's the northern hemisphere, this is 90 north. So the North Pole's out here, South Pole's down here, and here's the equator. Yet the whole Earth system, atmosphere plus ocean, is moving stuff to the north in the northern hemisphere, and to the south in the southern hemisphere. Through data products, we can split up the atmosphere and the ocean, the total, into the pieces that are done by the atmosphere and ocean circulation individually. So the green line here is the atmosphere's contribution to the energy transport, and the red is the ocean. So both are contributing to this general poleward transport, but different amounts. You can see in the subtropics and the tropics, the ocean and the atmosphere split the balance. They both contribute a lot, but that at the higher latitudes tends to be more of the atmosphere that's doing the bulk of the work. That said, just because the ocean's transport up at 40, 60 north is much, much smaller than the atmosphere, doesn't mean that it's not a key component, or that this little bit of red can't influence the green. So there's a theory out there that says that, well, this blue curve is pretty well set by how much sunlight is absorbed in the tropics and how much there's radiated away as infrared radiation, and that the particulars of this blue line get set, but the green and the red can interchange a little bit depending on how it's going on. So just because it's a small amount doesn't mean that the ocean's not an important part, because the ocean can influence how the atmosphere transports its heat and vice versa. So the way that this energy transport is accomplished, it's done by the atmosphere and the ocean circulation. So the reason we have weather and climate is because of because we've got this imbalance. So what our weather and climate is a result of this imbalance. And the other piece that really drives how our weather and how our climate is set up is the Earth's rotation. We could imagine if the Earth weren't rotating and we were heating the tropics unevenly compared to the poles, you would just flux energy away directly to the poles, and it would go straight there, and that would be not particularly interesting. But the Earth is also rotating, which gives all of our circulations this actual rotation of feature. And this is why when you look at weather systems, with the fronts on the nightly news, you'll see these big rotating features that have fronts going counterclockwise in our hemisphere. And that's why when we looked at the video at the beginning with all of the rich eddies in the ocean, they're all rotating also. In the large scale, because the Earth is rotating, it imparts rotation to everything else as everything else is working to move energy from the tropics to the poles. So that's I tend to think more in terms of thermodynamics and heat transport. So when I start looking at problems, weather and climate are consequences of our heat transport, because we have uneven heating and because we have rotation. And the particulars of weather and climate are certainly important, but those are all details in the grander, bigger picture of how our Earth system works. So when we talk about ocean circulation, in particular, if we're just thinking about the ocean today, we tend to divide our ocean circulations into two pieces. So the ocean is driven by the atmosphere in a couple of ways. One is by the wind, and the wind-driven circulation is what's at the upper part of the ocean. You can see in this schematic here, the upper gyres. So this is a larger scale. That video before was the smaller eddying field. These are the large scale, basin scale circulations. You can see in general, in the basins in the Atlantic and the Pacific, we've got these gyre circulations. So here's a subtropical gyre with the Gulf Stream going in this sense, and the subtropical gyre in the South Atlantic in the opposite sense, because we flipped over the equator, so everything switches sign. Same going on in the Pacific. We've got our subtropical North Pacific gyre and South Pacific gyre. A lot of complicated stuff goes along in the equator. Things are switching sign every which way, depending on what's going on, where you are. The Indian Basin is also pretty complicated. And the Antarctic Circumpolar current is always from west to east. So this is one of the ways that what's going on in the atmosphere affects the ocean and what gives us a lot of the features of our upper ocean circulation. The other piece that the ocean feels from what's above is in terms of temperature and salt. So temperature is being imparted where the Earth is absorbing energy, and that affects how warm and cold things are. And then salt is affected by the atmosphere giving us rain or evaporation. So if you have rain, you have less salt that gets into the ocean, or salinity, so it becomes fresher. And this affects how dense the ocean is, giving us what's called the buoyancy-driven circulation, also known as thermohaline circulation or the conveyor belt, or as we'll talk about in a second, the Atlantic meridional overturning circulation. So the buoyancy-driven circulation, in contrast to the wind-driven circulation, is mostly a vertical one. So these yellow areas here are where we have sinking motion in the North Atlantic, as well as in the Ross and the wet LCs in the Antarctic. This is where water goes down. And when you have water going down, it has to go somewhere. It can't just stay there. Otherwise things would bunch up and it just would stop. In the North Atlantic, what you have is this deep, these blue is like about 2,000 meters down. The purple is the very bottom of the ocean, 5,000, 7,000 or deeper meters. So you have this intermediate flow that at depth that goes down the coasts of the Americas, gets swept into the Antarctic circumpolar current, goes around a few times until something happens to kick it out. Either it gets kicked out in the Indian Ocean somehow, or it goes the slow path through the Pacific. And generally through the Pacific, through small scale motions, it gets gradually warmed and it gradually lightens and gradually rises back up where it gets to the top. And then it can go through the end of the Pacific basin and come through the Indonesian through flow, have a lot of time getting extra salty in the Indian basin, sneak around South Africa, and then go back up at the surface through the Atlantic basin to the high latitudes and repeat a circuit. There's a lot going on in the ocean. So you can imagine that our imaginary parcel that started in the North Atlantic and then traveled this entire loop, not every parcel does that. But if it were, it would take thousands of years to make that full loop. So it's a very slow circulation, but it's also a really important one because it's slow. Its slowness gives it predictability. So if we're thinking in terms of things of heat transport, as parcels are following along this part of the Gulf Stream in the North Atlantic current in the North Atlantic, they'll be taking heat with it and dropping that heat off in the high latitudes. And that convergence of heat is something that the atmosphere can feel. So that's why I'm really interested in the buoyancy-driven circulation, is because it's slow enough that we might have predictability that we can figure out what's going on with climate a couple of years in advance. So something worth mentioning about the buoyancy-driven circulation is that it shares features with the wind-driven circulation, especially in the Atlantic. So if we're paying attention right here, pay attention to the red, the surface flow, that's the same thing as the Gulf Stream. So the Gulf Stream is both part of the wind-driven circulation and the buoyancy-driven circulation. So it's doing double duty. And that's kind of where our first order scientific understanding of these things kind of breaks down, because some things are both wind-driven and buoyancy-driven. So it gets more complicated. Same going on in the subpolar region. There's a lot of really complicated stuff up here going on. It's both wind-driven and thermohaline-driven. So it just anytime you want to understand what's going on in the North Atlantic, there's a lot of extra considerations that need to be taken, because we have multiple theories that help us understand what's going on. So one way, if we take both our wind-driven and a buoyancy-driven circulation and say, okay, that's a physical way of understanding it, let's just average everything across the Atlantic. We're going to start on the West Coast and go to the East Coast and just average it in a way that we have, just the mean circulation from South Pole to North Pole through the entire Atlantic basin. When you do it that way, and you're looking at it kind of in this flattened sense, the circulation, we call it then the Atlantic meridional overturning circulation. Meridional generally means that it has a north-south component to it. So here's our slice. We're looking at our slice from the South Pole to the North Pole. So you can see that we've got this two overturning cells when we've taken our view of the ocean circulation in this way. We've got this upper cell. And so this part right here, that red arrow, that's the Gulf Stream again. It transports, you have your sinking motion up here in the North Atlantic. So that's these two zones right here. That's what's going on here. And then water flows in intermediate to deep depths. So we're about 3 kilometers down. then gets sucked back up in the Southern Ocean and repeats that cell in that sense. We also have this deep lower cell, abyssal cell, where we've got sinking in the Antarctic. So that's these two zones. And you have this especially deep water that's really, really heavy that sinks down and it's slowly heated back up such that it can make another cell circuit. This is sort of a mathematical way of looking at it. We've taken an average in the vertical.
Quick question, Elizabeth. Is the mid-Atlantic ridge just doesn't show up, or is it subtly shown in that figure?
Nope, there's no mid-Atlantic ridge in this figure because the mid-Atlantic ridge just sort of is right about here. And we've just tried to take an average of everything in the east-west direction that we have. So the mid-Atlantic ridge kind of vanishes in this view of it.
Sure.
So because the Atlantic Marine Overturning Circulation, or AMOC, does have pieces of both the wind-driven and the buoyancy-driven circulation, it means you can use both ways of thinking about it to try to understand what's going on. So something that oftentimes you'll go to a talk and they'll say, this is the AMOC. And then you'll move on and you'll stay at a really high level of the AMOC is important for heat transport. Heat transport's important for climate, blah, blah, blah. Thing is, this is what the AMOC really looks like. We can make these nice schematics that are very, simple, one overturning cell over another, but in reality, things are quite complicated. So this is a more recent schematic of where we think all the individual currents that contribute to that big overturning cell are. So for example, here's the subtropical gyre, we've got the Gulf Stream, but we've also got the Antilles current, these little other things going on. The subpolar region is especially complex. We have different deep water masses coming off from the Nordic seas. We've got Denmark Straitwater, East Greenland current. We've got all of these little wiggles. And when we're trying to understand in detail, like improving our climate models and understand how climate variability in this basin is being affected, the details of these little currents matters. And the exact placement of them matters. For example, these like teal colors or have the recirculation gyre, and where that recirculation gyre, how far south it gets or its placement in a climate model really matters for, and like if we're having heat waves in the Gulf of Maine. And so it's a reminder that in the bulk, we can, describe our circulation with really simple schematics like these, but it's actually a very complex system with a lot of rich detail that we need to keep into account, and means that I'm going to have a job for a while, which is great. But if we, think at the broadest scale, why do we care about the AMOC from a climate perspective? Why isn't it just some arcane thing that oceanographers like to go look at? It's because it's important for transporting heat. So this black line here is the global ocean heat transport. So this is earlier when we were looking at heat transport, that was the red line. So now this black line becomes the red line. And you can use climate models and observations to best split up how we think that heat transport is divided by the basins. And so we have in blue, the Atlantic basin, red is Pacific, and green is Indian. So what you'll notice is the Pacific is pretty evenly split. When you're on one side of the equator, you have heat going northward. When you're on the other side of the equator, you have heat going southward. Pacific basin is nice and symmetric. The Indian basin and the Atlantic, however, are not. The Atlantic basin is always moving heat northward. The Indian basin is almost always moving heat southward, including across the equator. And for the Atlantic basin, that's another piece of evidence for why we know the AMOC is there, because it's always northward. So remember, in the simple schematic here of the AMOC, heat transport is done at the upper part of the surface. So this red arrow is what's always moving our heat from the southern hemisphere to the northern hemisphere. And that has really important implications for climate. It's why we think that we get more rainfall in the northern hemisphere. It's why, at least in the Atlantic basin, people will often say, well, the reason we have a Gulf Stream, that's why Europe is warmer. So this whole blue line being above the zero is a reflection of that. So the heat transport, that's, partly, if it's always northward, that's why we expect Europe to be warmer than, say, British Columbia and Pacific Basin. So on human timescales, and by human timescales, I'm going to here say a couple of decades. What happens is we think that the AMOC converges heat in the northern North Atlantic as it spins up. So it's spinning up, it's getting stronger, it's transporting more heat to the northern hemisphere. So that's this red line here. It's strengthening, we're getting more heating. This whole area becomes more red. The atmosphere feels that. Anytime you've got heat moved somewhere, the atmosphere is going to respond, and it gives you this extra circulation where you have a low and a high. Now, as the circulation is strengthening and reaching its peak, you're going to have more energy that was transported into the high latitudes in the ocean that is going to be then fluxed out of the ocean basin into the atmosphere. So you're going to spin up and change the atmospheric circulation just a little bit more. And you'll see that, if it's a lot warmer there, this could be keeping Europe a bit warmer. But at the same time, this big warm anomaly is being transmitted back down to the subtropics through atmosphere and ocean processes that work together. And then finally, a couple of years as the AMOC is weakening, we don't have any more heat transport. We're just slowly letting all of that heat go back out to space, back out to the atmosphere into space, and the whole process slows down. And then we wait again for something to spin the AMOC back up before we can get another cycle through where you can warm up the ocean basin. And you can see very clearly for the Europe part of this, okay, this basin gets warmer right next to Europe. You'd expect this to warm Europe up. So this is the mechanism that's thought to be behind how the AMOC can be related to warmer winters in Europe. We don't have a similar circulation in the Pacific basins. The Pacific is much more symmetric. It doesn't have an overturning. So this process where the AMOC spins up, converges heat, the atmosphere responds, everything gets a bit warmer. Oftentimes we'll call this whole process Atlantic multidecadal variability. And it often has this pattern here on the right where just the entire basin warms up, with that warming really concentrated up in the subpolar North Atlantic near Greenland and the Labrador Sea and off the coast of Canada. It's also known, you may have heard it referred to as the Atlantic Multidecadal Oscillation. And it was given this title of AMO, oscillation, because this pattern up here over the best records we have from back in the 1800s, so thermometers, it has this kind of couple of decades swings back and forth. So we've got, 3 decades warm, 2 or 3 decades cold, repeated over and over. And so because it kind of had this back and forth behavior, folks called it the Atlantic Multidecadal Oscillation, thinking that it's some sort of wave. My best read of the literature is that it's not actually a wave. It's more of just a random process that happens to have that kind of behavior. So I really prefer the term multidecadal variability because it's a more general term that can encompass the AMO without saying if there really is some wave-like oscillation present in time in here. But that's just semantics. The important part is that every couple of decades, for whatever reason, the Atlantic basin warms up, and this has a whole host of the climate impacts that follow it. So for example, Atlantic multidecadal variability, when the Atlantic's warm, you get more frequent Atlantic basin hurricanes, you get more European heat waves and drought, you tend to have more rain in the Sahel because the atmosphere circulation is pulled northward such that you'll get more rain there. And these are all Atlantic basin impacts, but when we have positive sea surface temperatures in the Atlantic, so positive AMV, we also see changes in circulation around the world. For example, the monsoon circulation, the Indian monsoon is affected. So what happens in the ocean up by the Labrador Sea and Greenland and far north can a decade or two later have really important climate impacts around the world. And so this is kind of what gives me hope is for my career is that I can help out trying to figure out what's going on. And maybe, we'll be able to make predictions a decade out by the time we're at the end of my career. They won't be perfect predictions. This isn't going to be weather, But, you might be able to say, okay, are we more likely to have drought in the Sahel in 5 years or not? Can we improve the odds? And it really gives me a lot of hope and means I have a lot of work to do, which is great. The AMOC also gets a lot of press because it's often invoked as a way to explain what was going on in the deep past for the Earth. So over the last 20,000 years, for example, as the world came out of the last ice age, we have all of these little wiggles in our temperature records that come from ice cores. And one way that people use to explain it is, okay, sudden slowdowns or speed ups of the overturning in the Atlantic can give you changes in heat transport. And if you get changes in heat transport, that's going to affect sea ice. And if you affect sea ice, you're going to maybe have feedbacks on your ocean transport even more. So it's often paleoclimatologists love to use the AMOC as ways to explain theories. And so they'll kind of throw theories out there that usually have an AMOC link to explain what's going on. Based on paleoproxy evidence, as evidence, so in this schematic here, we've got this little star that represents one core from the ocean where they took protactinium, thorium, and they measured those, and they are best thought about in the last glacial ages for how the AMOC changed is that the AMOC has different modes. So currently would be what's called a warm mode, where we have a strong upper cell of our stream function. So here's our AMOC here, a strong upper cell. It's pretty deep. The stuff that's going on in the abyssal cell is a little further. It's more scrunched to the bottom of the ocean. But during the glacial age, is based on what evidence we have, one theory is that we have a more even distribution between our upper and bottom cells of the overturning. You can get more cold water all the way to the top of the North Atlantic Basin. And then some folks also think that there's possibility that when it gets really cold or you're in transition states, the entire AMOC can temporarily turn off until things are more favorable for it, in which case you'll just have this one bottom cell that takes over everything. So this is just an important context to realize that this ocean circulation, important for us on human timescales, has also had a really important contribution on climate evolving over the Earth's history. So just if I had to pick one way of saying what's the important bit, the Atlantic Meridional overturning circulation is important for weather and climate because it is a key player in the Earth's energy transport. And it's important on both human and paleoclimate timescales. If you affect a part of the circulation in the ocean and you do it in a way that affects where the atmosphere gets heated, you're going to affect climate both nearby and far away. And its variability will change, and you can potentially have predictability. So I want to pause here for a minute or two to ask if there's any questions before we move on and talk about how is climate change going to throw wrenches in all of this. Richard, do you want to moderate? Because I'm not sure I can actually do anything while my presentation's up.
I'm looking now. I see Julie is raising her hand. Shall I unmute you, Julie, or have you unmuted yourself?
I unmuted myself. I don't know if that works or not.
That's fine. Go ahead.
Okay. You mentioned the variability, the cycle of the AMOC, and I wondered if you explained already what causes that variability.
So what causes this variability?
Yes, in particular that.
Yeah, so slide. I'm in the camp. So we don't have long enough observations to tell us for sure, because this thing takes 60 years to repeat one cycle. This is the best we can say with temperature records. And going back before this over here, our thermometers aren't so good. So everything back here should be really trusted very little. And really, the gold standard for observations doesn't happen until 1979, and that's the satellite era. So when we started putting satellites up, that really improved our observations. So we can really only trust really well the observations from 1979 forward, which means that we can't really say what's going on, but we can use climate models to try to understand what's going on. And based on a lot of climate model evidence, there's a couple of ideas. One is that whenever you get a strong wintertime jet coming across the North Atlantic, this is going to cause sinking in the ocean. And if you've got sinking in the ocean, this will spin up the AMOC and set this whole chain of events off. And that jet behavior is just kind of random. Just, sometimes it's really strong. And if you get a couple of strong years in a row, you can spin up the AMOC, but there's no necessarily oscillatory behavior to it. Some people also in their climate models will see after this kind of spin up happens, the ocean circulation spins up further in a way to reinforce itself or to switch to the opposite phase. In the literature, it's just all over the place, the kind of mechanisms you can get. But we always have to take that grain of salt that climate models aren't perfect. And and while they all can show this kind of behavior, what we really need is a longer observational record that we can trust. And we're just not going to get there for a couple more decades.
I know you're going to talk about climate change in the second half of your talk, but in that chart that you had before with the red going up and the blue going down, and it looked cyclical, and you said that you didn't, yes, that's the one. You said that you didn't really believe it was cyclical because we can't really trust the earlier data. But the climate change deniers are going to say, well, look, it was down before, it's up now, it's going to be on its way down again. So why are you so worried?
Well, this right here is not global temperature, even Atlantic temperature. This is the index for the AMO or AMV. And when you remake this index, you take out the global warming signal. So if we were to include all of the temperature effects on this one, you would see this great increase at the end here since the 60s and 70s.
Okay.
Whereas this is just sort of like giving you this up and down wiggles in the upward, generally the upward trend. So yeah, it has a cycle, it's a cyclical, but it's not, I'm kind of in the camp where it's a noise force process. It's not something that we can say for sure if it's actually like a wave that, the wave goes up and it goes down. And the reason it goes down is because it was driven down after it went up. I don't know if I don't really know if we have that kind of driving behavior or if it's more just randomly forced by how the jet up in the North Atlantic is feeling every other year. And I mean, the jury's really out on that one. It's going to take more observations to be sure.
Okay, thank you.
We have another question from Tom Eggert who asks, why doesn't the Pacific also play a role?
That was my dissertation. So the Pacific doesn't play a role because it's fresher than the Atlantic basin. The Atlantic basin is saltier and it's a bit, and because it's saltier, it means that you can get sinking. For things to sink, they have to get dense. And water in the North Pacific just isn't as dense. So because you can't get sinking, you can't get a circulation to form that gives you that overturning cell that's so nice. And so it doesn't play as an important of a role. The tropical Pacific, however, is probably the most important climate variability place. So it may not have this sort of long time scale thing, but with El Nino Southern Oscillation, that has an impact on climate everywhere, and it's much stronger impact, I would argue, than what's going on in the Atlantic.
When you said fresher, you meant in terms of salinity?
Yep, salinity.
Okay, yes, not geologically. Okay, fine. All right, thank you. Let me see, I think Bulent Atale has a question. Bulent, do you want to unmute yourself and ask it?
Yes, I think I'm unmuted now.
Okay.
It's known that 320 to 350 years ago, during the scientific revolution, there was a mini ice age with temperatures 1 or 2 degrees lower than it is now. What would that large variation just 300 years ago have been due to? Any idea?
Yeah, that's a tough one. We don't really have, obviously we don't have thermometers back then and we didn't have satellites, so it's hard to tell. One possibility I've heard is that we could have had a couple of years with a lot of volcanoes. So volcanoes will put lots of little particles in the air that reflect away sunlight and make everything a bit colder. So that's one possibility. And if you make the whole planet a bit colder, then that's going to affect ocean circulation, which can act as a feedback potentially. A lot of that's, yeah, if you ask paleoclimatologists, I bet they'll have a few more examples, but that's, I think, definitely one that's up there is volcanic activity.
Okay, George Erickson has a question. George, do you want to unmute yourself?
I think I am.
Yes, I think so.
Okay. On the image that shows an average depth from pole to pole, I have a question. Can you bring that up?
This one?
This one, yes. I found it striking, and I'm wondering if you have any comment on it, that the fact that the maximum depths, two depths shown for the ocean, are thousands of miles apart, yet they're virtually identical. That seems to be, quite a coincidence. Is that just an oddity, or is there some reason for this?
You mean in this schematic here?
Yeah.
Yeah, that's just the schematic. If you give me a sec, I could pull up an ocean bathymetry plot. It's the ocean bottom's a lot more complicated than what this conceptual schematic shows. So that's
Okay.
just coincidence.
Okay. All right, maybe we can go on then. Those were good questions, and I'm glad you had them now, Elizabeth. So let's move on to climate change.
Yeah, I like breaking things up. I teach twice, 3 times a week, and
Okay.
an hour just doesn't do very well.
Right.
One person talking the entire time. So what we know is that we've been emitting greenhouse gas emissions as part of since the industrial age, really. So we have here on the left, just to orient everyone, is the amount of global carbon emissions that we've had from fossil fuels since about 1900. These estimates come from the EPA, and it's really been increasing. This is per year. And this is the greenhouse gas emissions by different types of greenhouse gases. So carbon dioxide makes up the bulk of it, whether from changing how you have a forest and how much carbon is taken up by forest or not, or just more directly by burning fossil fuels and combustion. Methane also has an important part to play. Methane's a much stronger greenhouse gas per molecule, but we don't have as much up there, thankfully. Nitrous oxide and then other gases. So I kind of take a heat transport and energy transport kind of way of looking at this. And so if you put in a greenhouse gas, it's going to change up the entire energy flow in the planet. So if you change up the energy flow in the planet, everything's going to respond. So let's just talk, quickly about what are some of the impacts from the ocean's perspective of carbon dioxide. So the whole ocean, we'll get back to the Atlantic in a bit. On the chemical side, so not even talking about global warming, if you increase CO2, you're going to change the ocean's chemistry. And this is something known as ocean acidification, which we'll talk a little bit more about. On the physical side, carbon dioxide increases the amount of energy that's absorbed by the atmosphere. And this is going to warm the planet. And that warming of the planet is going to affect the transport of energy throughout the entire system. And if you change that up, then you're changing up your weather and climate as a response. So you're changing the balance of energy from one place to the other. And when you change that, the atmosphere responds and you change up where you're getting precipitation or evaporation. So what's known as the freshwater balance. And then from all of these, little subtle changes, it might be subtle from the planet's point of view, but from our point of view, it's quite big. You have all sorts of other climate impacts that we're familiar with. So both these chemical and these physical impacts of CO2 emissions are going to affect society, and in some cases already are affecting society and ecosystems. So let's talk a little bit about ocean acidification, since that doesn't get talked about quite as much, and yet it's just as big of a deal as global warming and has the same root cause. So what happens with ocean acidification is you have extra CO2 in the atmosphere, it gets absorbed by the ocean, and this changes the balance, the buffering of the solution in the ocean between carbon dioxide and how much bicarbonate ions you can have. So basically, carbon dioxide turns into an acid when you increase more of it in the ocean. And if you look at pH, it's kind of a little subtle change. It looks like you've only gone down maybe 0.1 or 0.2 of a pH unit so far. But in reality, we've changed, percentage-wise, 20 to 40% the pH of the entire ocean. And this affects marine life. So any kind of plankton species that uses calcium to make its shells, make the ocean a bit more acidic, they can't make their shells as well, or their shells are degraded. So any kind of calcifying plankton just won't be able to do that anymore. And because these are at the base of the food chain in the ocean, it can really have an impact that we're not sure what it's going to be on the rest of the ecosystem. So it's something worth keeping account of. Certain fisheries we expect to be affected also. So anytime you have like different types of shellfish that require calcium to make their shells, they also are probably going to be impacted in different ways. And the ways that ecosystems are going to be impacted, it's a hard thing to study, right? You can't just go take a whole piece of the ocean and make it more carbon, increase the carbon dioxide to see what'll happen. You just can't control that. You can't put that experiment together as well. So it's a tough thing to study. And there's a lot of really good research going on right now to try to figure out what could happen if we don't stop emitting carbon dioxide. And then on the physical side, increased greenhouse gases warm the planet. And so this is one of my favorite points to point out to atmospheric scientists, is that we've got all this excess heat from greenhouse gases. The ocean is absorbing 90% of the excess heat from the greenhouse gases. That is warming the surface here, warming our land and atmosphere, is 5 to 10%. It's like the atmosphere is roughly 5%. Sea ice is another 5%. So the oceans are really doing us a favor for the time being by sucking up all that heat and starting to sequester it at depth. But it won't be able to do that forever. It can only do that while things are out of balance. So yeah, here on the right here, we've got our best estimate of the Earth's total heat content from 1950 forward. And if you divide it by ocean versus land, the ocean is really doing us a big favor. And this is also why, even if today we were to stop emitting all greenhouse gases, we would still have some future warming ahead of us, because this heat that's gone into the ocean is going to come back out eventually. So even if we were to stop today, there's still be a little bit of warming in the pipeline that we would have to adjust to. So we really should start doing something now if we don't want to warm up too much more. And so this physical warming of the ocean is already having impacts on ecosystems and climate. One good example of an ocean impact is coral bleaching. So in some parts of the world, there are coral reefs that are being pushed out of the range of temperatures that they can thrive at. And so when the coral polyps get too warm, the algae just can't make it anymore. So the whole thing bleaches as the coral polyps die. And so you'll be left with images like this in the shallow seas where you've got these dead corals. There's a lot of interesting research going on right now. They find in some places you've got coral communities that are a bit more resilient, where you've traditionally had more variability in cold and warm waters that slosh over them. And they're finding that perhaps some of those communities might be able to tolerate greater warming in the world, or they're not going to warm up as much because of just where they're located. But in general, this is something that's already happening, and most of the coral is starting to bleach whenever the marine heat wave comes overhead. Then another impact that's definitely starting to happen already and starting to be noticed is we're having sea level change. So when you have heat in the ocean, water expands when it gets warmer. Water expanding means that sea level is going to rise. And so about 2/3 of the amount of sea level rise that we've already seen, so roughly 20 centimeters over the last 2-ish decades, is coming just from warm water expanding. About 1/3 of that sea level rise is also contributed to the fact that we're melting water that was on land, and it's trickling off into the ocean and adding sea level that way. So when you melt glaciers or ice sheets, things that are on land, you're going to also contribute to sea level rise. Melting sea ice doesn't contribute to sea level rise because sea ice is like an ice cube in your drink. It doesn't change as it melts. It doesn't change the level of the water. And incidentally, there's lots of great resources out there about melting glaciers. Like 95% of the world's glaciers are all melting simultaneously, which is not something you would expect unless you had a kind of impact, a kind of effect like global warming going on. So yeah, sea level rise is going to be a big issue because so many of the world's population live on coasts. And 20 centimeters for now might not seem like much, but coastlines generally are very, very shallow along the beach. So 20 centimeters vertical is more like maybe, 5 to 10 times that length in horizontal. So 20 centimeters might be equivalent to, 5, 10 meters of horizontal beach length, depending on the slope of the beach that you're at. And there's a lot of other issues that come from sea level rise. For example, in Florida, they rely on aquifers, and aquifers are below the surface. As sea level rises, you're able to get more seawater intruding into the water that's in the interior and the aquifers, and you can't drink seawater. So that this is a problem that they're starting to deal with, is the water is becoming saltier that they drink. Okay, so let's go back to the Atlantic, since that's something that every couple of years, well, in 2004, remember there was a couple of things that happened. One of which was there was in the scientific community a wondering about abrupt climate change. Could we have these so-called tipping points where we could, within a decade, really quickly, suddenly our climate shifts to something very dramatically different. And then 2004, there was also Day After Tomorrow, which gave this scenario, which was totally implausible, that the Gulf Stream shut down. And because it shut down, the world went into a new ice age, which is they basically took the paleo situation that folks think happened, millions of years ago, but not millions, but 10,000 years ago, but over a couple of hundred years. The movie showed it happening over a couple of days, which is just totally not realistic, but it got into the public consciousness. So over the last 2 decades, there's been a ton of work trying to figure out, is that possible? Can we have abrupt climate change? And because the AMOC is such an important piece of the global energy cycle, what happens how are greenhouse gases going to impact it? And how is that then going to impact everything else? So based on a bunch of different studies and different ways of looking at it, our theory is that the AMOC, at least in the North Atlantic, so what's going on in the Atlantic, it's going to decline due to buoyancy forcing. You're going to have a fresher North Atlantic because ice sheets are melting, sea ice is melting, and we're also supercharging the hydrologic cycle. So we're going to get more rainfall up there a little bit too. And that should all act to freshen the North Atlantic, making it more like the Pacific. So it makes things harder to sink, and that should slow down the whole circulation. And because that's going to slow down the circulation, you're going to slow down the amount of heat transport you have, and the atmosphere will respond to that. And then you can have a whole effect globally and in the Atlantic basin. So that's the theory, at least. We have 2 main ways of trying to figure out what's going to happen. The first is observational monitoring. Okay, let's, as best we can, watch for changes going on directly in the ocean. And then the other strategy we can use in tandem is climate model simulation. Our observations only go back so far, but we have these great climate model simulations that we can simulate the past to fill in the rest of the blanks, and we can use them to predict future changes. We'll talk a little bit about that in a second. So the gold standard for observing the AMOC is what's called the rapid array. And it's this set of moorings that stretch from the western side of the Atlantic basin to the eastern side at 26 north that they put in 2004, at about that time when we were all wondering about abrupt climate change. So here's a section at 26 north, and each of these little red and yellow dot lines is a single mooring that they put in. So you can see we don't have moorings across the entire ocean basin, but they tried to put a mooring at each where they thought was most important. So you have the Gulf Stream and you have the deep western boundary current here on the western side. So that's why we have a lot more moorings in there. You have a lot less or weaker currents through the interior of the ocean. And so you tend to have just a few moorings here and there. And so you'll notice that we don't have observations that are tight across the entire of the basin. We have a couple that tell us a lot, but it's still not everywhere. And this is a very expensive project that's been international. Mostly the UK and the US has been contributing to it. And it really has, because we now have all these moorings, we can estimate how much total transport do we have by the AMOC at 26 north. And this record goes back to 2004. So we're starting to have a couple of decades. And it's really been an important part of the scientific thrusts in the AMOC community for the past decade or two. So this is our best observation. This is what everyone compares against, what's going on at 26 North. So this is very recent paper where they're trying to use that observation at the rapid line. And we have 3 different ways of looking at it. On the top, we've got every 10 days averages. In the middle, we've got the seasonal cycle at 26 North. And then the bottom one is if we're taking out the seasonal cycle from our high frequency 10-day band average. So we've got this sort of low frequency, smooth time series of the strength of the AMOC. So what we can see is that we think there was a little bit of dip at 2009, but that dip is slowly recovering. And based on what we know has been happening further north in the basin, we're expecting that this should be continuing to increase a little bit more for the next couple of years. And so something that's important to point out is that you can see this dip right here maybe was a couple of sphere drips, but which is the unit that AMOCs are measured in, don't ask. But if we look at the day-to-day, the weather in the AMOC, you can get these sudden, 10 to 30 and then back down variations. Whereas in our interannual, you could just sort of see these smaller variability that's just not as pronounced. And that was, I think, one of the biggest results from the RAPID project was just how much sharp weather you can get in the AMOC that we didn't expect. We were expecting, I think, something more like this, slowly varying. But in reality, this is what it looks like, a lot more weather going on. So the best, my read of the literature is, especially based on this one, is that it's really too clear, it's too soon to tell if we're seeing a greenhouse gas forced signal at RAPID. And that, remember, RAPID is at 26 North, so that's pretty far removed from the places that where sinking occurs. And that sinking is an important part of what we think will be affected. So it's a little too soon to tell if we're seeing a decline yet or not. That's also partly why they put in another array further north to try to monitor what's going on in the places where sinking occurs. So sinking for this circulation happens, we think, in the Nordic seas mostly, but then there's also a contribution in the Labrador Sea. So they put in another NSF, and then the UK also contributed another, and I think a bunch of the other European countries also have components on this, a bunch more moorings across the Labrador Sea and across the open subpolar North Atlantic. A bunch of more moorings. They've also got some fun gliders going back and forth. Here's the schematic of the glider, and it's taken temperature profiles. This goes back and forth to try to measure a bit more specifically all of these complex currents that are going in and out around Greenland, in the Nordic seas and the Labrador Sea. And so this one's only been going since 2014, and I think I've only seen published results since about 2018. So it's too short a record to tell anything yet, but it's already scientifically, besides the greenhouse gas question, been really interesting. For example, climate models say the Labrador Sea is where it's all at, but the OSNAP array says actually it's over here. That's where all the important stuff's happening. And so it's really giving us a way to help improve our climate models if we believe that these 4 years so far, 2014 to 2018, are representative of what's going on. So yeah, this program's been really awesome to see. And I'm hoping it's going to be continued a while yet longer so we can get a record that's actually long enough that we can say something. So the other tool we can use are climate models. And so what you do with climate model is you take Newton's laws, so F equals ma, force equals mass times acceleration, and you take thermodynamics and you break it up on a grid and you apply at every single point those equations. And then for the things that you don't fully understand, like clouds are a big one, you come up with your best guess of what the dynamics in clouds will be. And then at each little grid point in here, you solve all of the processes that are going on, both in the atmosphere and the ocean, as well as with sea ice, land processes. Some climate models now we're using the word Earth system models for them because they also include biology in them. So they'll have a representation of plankton in the ocean. And so you take all of those physics and biology and chemistry and you slowly integrate it forward in time. So you use a numerical method and you say, okay, we're at this point in this time. We're going to use all of our, all those processes, chunk them through the next time step. And then we'll start again and again and again. These climate models are, effectively the same thing as weather models, just use slightly different versions of parameterizations, or you have bigger grid cells in the climate model, because weather models usually aren't as you don't necessarily need the whole globe, whereas for a climate model, you do need to include the whole globe. So what do climate models say about AMOC? This is the most recent set of climate models. Each little block is one climate model, and then you run the climate model many times to try to get a representation of what all the possible natural variability futures could be doing. And so what you can see is that all models suggest there will be a decline in the AMOC by 2100, but not a collapse. So a collapse would be we go to zero. None of these go to zero. So that's what we think is going to happen, but there's a very different rate. So for example, let's look at, say, CNRM. This model right here starts at 16 sphere drips, and within 20 years, we're down to 12, and that range of variability is very small. So you can see that if we lived in the world for this climate model, CNRM, you would expect to see the AMOC declining now. You would see it. But for example, maybe we are actually in the world that the German model, MPI. And so 20 years in the future, we've got so much variability in their AMOC and not much decline that 20 years from now, we may not be able to say, has the AMOC declined because of greenhouse gases yet, because the variability is just too much larger. Which climate model is correct? Which ones, or I guess I should say, which is less wrong? That's a great question. There's a quote that I use in my classes by George Box. All models are wrong, but some are useful. Some of these models do a better job at simulating the present climate than others do. We tend to trust those models a bit more, because if they're doing today better, then they're probably going to be doing tomorrow better also. But there's a lot of things wrong with these models. All of that complexity I showed you in the North Atlantic, most of these do a pretty terrible job at it. But they do all agree that the AMOC should be declining, not necessarily agreeing how much or when we're going to see that change. But it will decline if we continue emitting greenhouse gases as we have been. So something I think worth pointing out, so we, this day after tomorrow, like, oh, the greenhouse gases, it's going to cool off Europe because the Gulf Stream collapsed. That's not going to happen. I mean, the Gulf Stream, sure, it's an important part of the heat transport, but global warming is directly warming the climate so much that any small change you get from the Gulf Stream weakening is going to be far outweighed by any direct effect of greenhouse gas warming. So it's important to understand, because it's going to potentially affect the details of circulation, but it's the direct greenhouse gas effects are much larger than any AMOC influenced indirect effect. So for example, here we've got a figure, 4 different sets of different scenarios. And the width of each of these, each little dot represents how much variability of the temperature you can attribute due to the AMOC. And then each color is how much greenhouse gases you've put in. So this blue one up here, which has the most warming, that is if we continue on a business as usual scenario. We keep emitting greenhouse gases like we are today. And you can see that that amount of warming in the global mean, 3.5 Kelvin, is way larger than any spread you can get due to the AMOC of maybe, a couple, 0.1 degree, a little bit. So like, and if we're on the y-axis, maybe you've got 0.2 of a degree Celsius versus 3 degrees. So it's just, it's important to understand how the AMOC is going to change, because there's a lot of details that are important. But Europe is not going to get colder if the AMOC collapses. Well, not collapses, the AMOC slows down. Europe is going to warm up because greenhouse gases are increasing. So I wanted to end with, every couple of years, there's a big AMOC article that comes out in Science or Nature. So those, the big high profile scientific publications. So every 2 years, there'll be one on the AMOC, it seems like, and then the popular media will pick it up. So I figured, since some of you have probably seen this in the news in the last 2 weeks, there's been some really nice articles. The New York Times was pretty good. The Washington Post article was pretty good. CNN was not particularly good. This is the article that they were all picking up on, this new Caesar et al. Paper. And what they did in this paper was they're trying to place changes in the AMOC in context. And so they're using all these different paleo proxies. So they're drilling mud cores, ice cores, whatever they can get their hands on at each of these individual locations. And then they're putting them all on one plot to try to see, all these different metrics for AMOC. And what they find is that they all seem to be decreasing over the last millennia or two. And that they all seem to agree that we also seem to be seeing a decrease over the last couple of decades too, with a slight increase in the 1990s. Yeah, it's a nice full article that does a lot. But in general, I tend to be very hesitant with paleo proxies because you're not measuring the AMOC directly. You're measuring something that you think is a good stand-in. But all of this seems pretty consistent with what we expect will happen. Is it really happening now already? I think that'll depend on how much you trust the proxies. And that's not something I can really talk on because that's not my area of expertise. But definitely check out the New York Times article if you haven't yet. It's got some really great graphics. So, we'll wrap this up. The Atlantic Ocean circulation is a key part of the Earth's energy budget. Climate influences it, and it then influences climate. So it's a key part of our global system of weather and climate. Greenhouse gases are already having an impact on the oceans. They're warming, sea levels are rising, the oceans are becoming more acidic. And these are just a couple of the impacts that we know are happening already. And the Atlantic Ocean circulation is projected to weaken due to greenhouse gases. And it's really important to monitor it to see how individual local impacts are going to shift. But these are second order kind of impacts compared with the direct ones due to greenhouse gas emissions, like sea levels rising or just everywhere becoming warmer. So with that, I'm happy to take some questions for the rest of the time. Thank you again for listening.
That's great, Elizabeth. I really appreciate that. I think it's a pleasure for me personally to see this elaboration from an expert in the field and a review of climate change effects on AMOC. We've talked about AMOC a couple of years ago, but it was my superficial knowledge of it and your expertise, as well as bringing us up to the date. It's really been wonderful. We have a question that we didn't pick up before the break from Lee Gasper Galvin. She asks a good biological question. I'd be interested on your thoughts. What do you think is most likely killing coral reefs? Is it pollution, acidification, or temperature change?
Temperature change.
How much?
I've had that before.
Change?
Why don't you think acidification is part of it?
Well, this is stepping a bit out of my area of expertise,
Sure.
But what I've heard from my colleague who does do coral bleaching, it's a temperature thing that's
It's a temperature, okay.
primary. Those are also acidification and pollution are definitely stressors.
Okay.
But you get these coral bleaching events when the local waters get really warm,
Okay.
and then they don't
So-
come back.
So
Now,
how much temperature change are we talking about?
Yeah, degree or two maybe. Temporarily, it only takes a little while to bleach them, and then the waters will come back down to a normal temperature, and it's too late.
Wow.
But they'll recover a couple of times, but after 3 or 4 bleachings, they often die permanently. Would you agree with
Sometimes
that?
it just takes one.
Really? Okay.
It depends on where you're at, the species of coral. There's
Sure.
some species that are more resilient and can handle these kind of things better, and there's some that aren't.
Okay.
Like my colleague, I used to work at NCAR, and there was this wonderful scientist, Joni Klapis, and she does corals. That's her expertise. And she would go down to Costa Rica, and they would transplant corals from communities that they thought were more resilient, and they would try to see if those new communities would last in warmer waters. And it sounds like they're having some success, though you can imagine this is a very intense way of doing it. You have people going in and planting corals directly
Right.
to see
Yeah.
if they can get a new community started.
Would you answer that question, if I can interject? Lee. I'll let you get back if you have some more, but could I modify Lee's question by asking, what do you think is more threatening to krill in the Antarctic oceans, temperature or acidification? Would you change your answer for that?
That's getting beyond what I can. I'm not a biologist.
But
From what I know of krill, I don't think they're calcifiers as much, but depends on what they're eating, and
sure,
I can't really answer on that.
Okay. Well, we won't hold you to that because it is a difficult one. But yeah, and I think you gave us a big point that we have a lot of resilience in the oceans building up, and it's going to take a while to rectify not only the temperature but the acidification.
Well, there's some places where there's resilience, and there's some places where there's not. And hopefully we, at least in terms of corals, maybe we can find the places where there should be more resilience and, conserve those places more.
Right. Did you have residual questions, Lee, or did that answer your?
No, that takes care of it. Thank you.
Okay, sure. Any other questions? See any yet? We've been, I think part of the reason that we're not getting more questions is that you're so thorough and you really covered a lot of the potential questions. It's a fascinating topic, and I really appreciate your putting it together for us. So if
I think I see a couple of questions, or at least hands raised on my end.
Okay, let me, do you want to try them?
Sure, if I can hear them.
I think they're the same people who we've already answered. Lynn Green has one. Any feelings about wind turbines in the ocean? Yeah, that's a great question. My wife asks me that all the time. Well, don't you think the wind turbines the vibrations are going to affect the fish? But that might not be in your answer here. What are your thoughts about wind turbines in the ocean?
That's definitely outside my area of expertise, and I can't say anything about the biology, but I can say in terms of renewable energy. And if we're going to start decreasing carbon dioxide in the atmosphere, our emissions, we need those kind of technologies to help get us out of where we're at.
I addressed it a little bit last week. I talked about if you have offshore wind turbines and you pound concrete foundations into the bedrock offshore, that can be very disturbing to the fish, to the whales, and so on. And then if you wanted to be a little gentler in terms of sound transmission through the oceans, you might want to consider floating rafts with wind turbines on them, as opposed to burying them in the bedrock. That might get us around a little bit the problem of wind turbines. But yeah, that's a biological question. But
yeah, that one, or in engineering. So you've got me on both sides.
Right. Okay,
it's interesting. Like, I'm now starting to build my group up, and I'm interviewing grad students and things like that. And just my experience around grad students who want to go into climate science, a lot of them want to go into it to save the planet. Yeah, climate change is a big problem. I want to, understand the science. And if you want to save the planet, you don't go into climate science. We already know enough about how things are going to change to first order. I mean, we can always go and study more important little details, but if you want to save the planet, you go into engineering, because those are really the kind of technologies that we need to get us out of this mess. So it's always amusing to me when I see these students like, yeah, climate change, big problem. I want to understand it.
Yes, indeed.
Okay.
Good point. Lee has another question now. Considering the wide variability of temperature, for example, from -15 to 100 degrees Fahrenheit in Wisconsin over a year, why is a 1 or 2 degree temperature change globally so much more concern?
Sure. So I think the way I like thinking of this is, it was only, I think, like 4 degrees Celsius in global mean between us and the last ice age.
Yeah.
So if we're thinking in terms of the whole planet, locally, yeah, we have a ton of variability, year to year. But in terms of ecosystems, especially in the ocean, where you really have very steady temperatures, it doesn't take much to change things up. Like for example, in terms of fish, I remember seeing this one study where you can already tell that fish are starting to migrate deeper into the ocean where it's colder, because biologically that's where they like to be. So yeah, 1 to 2 degrees may not seem like much, but if you put it in context of ice ages, that's 25 to or more % on your way to like warmer compared to where you'd been at the ice age.
Yeah, there was a mile of ice here a few 100,000 years ago, or tens of thousands of years ago, when the average temperature was only a couple of degrees cooler. We were under a mile of ice, so good answer. Any other? I think Rika has a question, or comment, and I'm glad to pass that along. She says, "Thank you very much. Very interesting and clearly represented." And
Thank you.
Wholeheartedly agree. Yes, thank you for that comment. Well, it's 11:15, and we don't have.
Or ice cap question. I'll send.
I'm not. But
Are we having some more questions that we're missing?
I see Dr. Adelaide's hand and Ms. Patel's hands up. Maybe they have another question.
Fire away. I'm not seeing them at the moment.
Hello?
Buland.
Yes, Dr. Maroon, I wanted to thank you for a wonderfully illuminating talk. I get the Oxford University Physics Department publications, and they published 150 years of temperature change, which coincides with the period that fossil fuel burning ships cross the oceans. And it fits very nicely the data you showed that starts with 1900. They're both exponentially rising curves, although of course it depends on the scale, but you do see the exponential rise. But thank you again for a wonderful lecture.
Yep. Thanks so much for coming, and thank you. Yeah, temperature record. There's so many people poring over just that one time series that you described, since with our best guess going back to 1900 and trying to understand every little wiggle and what's meaningful, what comes from the Atlantic, what comes from the Pacific, and most of it, how much of it's fossil fuels, which is the last couple of decades, a lot.
Dr. Atalaya is joining us from Fredericksburg, Virginia, and will be our speaker next week on fusion. So we will look forward to that engineering aspect. It's a challenging field for all of us to keep track of, and Dr. Adelay is an authority in that field. So we're really looking forward to your talk, Dr. Adelay, and thank you for joining us today.
Thank you.
And thank you again, Dr. Maroon. It was really a delight. And if you ever need a letter of recommendation to your chair, don't hesitate to ask me for one.
Oh, thank you.
Okay, you have a great week, all of you, and we'll look forward to Dr. Atalay. I have a few things to share with the group online, which I'll do. So good to see you all today. Enjoy this weather here in Madison. We're talking about possibly 50 degrees and maybe 60 by tomorrow. So there's a rapid increase in our rate of warming here atmospherically in Madison.
Thank goodness.
Okay, bye-bye now, everybody.